following video is on parallelism of vectors. So let's look at the first one. So A is a vector of 2, -1, 3, and B is a vector -6, R, S, and these are parallel vectors, and I want to find R and S. Well, if they're parallel vectors, then they're going to be proportionally the same. So there's some scalar that I need to multiply to one vector so that it equals the other vector. So I can see here that I'm going to multiply by -3. If I multiply, if I have a scalar of -3, then -3 times this vector will give me this other vector. So -3 times 2 gives me -6. This is really where I made that connection, right? If I have 2 times some scalar equals -6, because these have to be proportionally correct, then this k has to be -3. K has to be -3. So -3 times 2 gives me -6. -3 minus 1 is going to give me, that's going to give me 3. So R equals 3. And then -3 times 3 is going to give me -9. So S has to be -9. All right, let's look at number 2. It says, find the scalar AB, given that these two vectors are parallel. Same thing, there has to be some scalar. I'm multiplying something, some k value here to get, let's look at what we do have. It looks like our y values. So I have some scalar times -1, and that's going to equal 2. Well, what do I need to multiply here? K has to equal what? Well, -2. -1 times -2 is going to give me 2. So that's my scalar. K has to be -2. So 3 times -2 is going to give me, 3 times -2 is -6. So A equals -6. And then my B value, if K is -2, so -2 times 2 gives me -4. So B equals -4. So those are my values here. What can be deduced from the following? I have this vector here of AB, and it equals 3 of this vector CD. Well, that means if they are equal to each other, then these must be parallel to each other. Vector AB must be parallel to vector CD. That's one thing we can deduce. Another thing we can deduce is that vector AB is, well, I should say, that 3 times vector CD is going to give us vector AB. So what we're saying then is that this CD vector is a third, right? It has to be a third the size. We're taking this vector, multiplying it by 3 to get this other vector. So that's the other thing we can deduce, is that that this vector CD has a magnitude a third of what AD does. So has a magnitude 1/3 of AB. That's what we can deduce. All right, looking at this one, we know if these equal again, if these two vectors are equal, then we know that these vectors have to be parallel. So vector RS has to be parallel to vector KL. We also know then that if we have to multiply, well, if this vector here is negative, it means that KL is, the vector KL is going in the opposite direction. Is going in the opposite direction, to RS. And then we also know if I'm multiplying some vector here by 1/2, then it means that this vector here of KL is twice the vector of RS. KL is twice the size, is 2 times RS. I think this one's sort of interesting. I wasn't thinking I was going to do it, but I might as well do it anyway. If we have this vector A to B, so I have vector A to B, and then we have another vector from B to C, and these are parallel, well, then they occupy, that all A, B, and C are going to occupy points on the same line. We call this, when points all occupy the same line, we call this collinear. So A, B, and C are collinear. All right, moving on. Number 4, so I have the position vectors P, Q, R, S. We have all these. This is P, Q, R, and S. And these are position vectors, so the tail of our vector is at the origin at 0, 0. So there's some point that, so we have this R vector from the origin of 0, 0, 0. And then it just branches out 3 to -1, which means this point here, then whatever the point is 3 to -1. -1. We have the same thing here when we have, so let's do R. R is going to be this one here. So we have some vector here of, it's a position vector, so the tail is at the origin, and the vector goes 2 in the x direction, -1 in the y direction, and 2 in the z direction, which means this point here is going to be 2, -1, 2. So our vector from, so this particular line, I guess they want this line right here. It wants us to deduce that this line here and this line here are parallel. So it doesn't matter what direction they're going. Let's find our vector then. Let's do head minus tail. Again, direction doesn't matter. So we're going to do head minus tail. So we're going to take R. This is P, Q, R, and S. I'm going to take R, which is 2, -1, 2, and I'm going to subtract that from our tail of P, which is 3, 2, -1, giving us 2 minus 3 is -1, -1 minus 2 is -3, and 2 minus negative, that's a positive, 2 plus 1 is going to give us 3. So let's look at our other vector QS, so head minus tail again. We have -1, -2, 3, and we're going to subtract that from the tail, which is Q, which it would be 1, 4, -3. To get -1 minus 1 is -2. -2 minus 4 gives us -6, and 3 minus negative, that's a positive, so 3 plus 3 gives us 6. Now the question is, oops, I'm sorry, you didn't see that part. The question is, are these scalar multiples of each other? Is there some value that we can multiply this vector to for each of these components to get this vector? Well, yeah, what about 2? What if k equals 2? Then 2 times -1 gives us -2, and 2 times -3 is going to give us -6, and 2 times 3 is going to give us 6. So these are scalar multiples of each other, so they have to be parallel. They looks like they are going in the same direction as well, which doesn't really matter when we're just talking about lines anyway. And parallel vectors don't have to be going in the same direction. They can also be going in opposite directions. All right, so then it says, what is the relationship between the lengths of these PR and QS? Well, the relationship is that, well, to me it looks like this QS, this length here of QS, is twice the size. This length here is twice the size of PR. So let's look at 5a. If I have this vector of a, which is -4, I want to write a vector that's going in the same direction as a, and it needs to be twice its length. So if it's in the same direction and twice the length, I'm just going to multiply by a scalar of 2. That's going to give me 4, 8. A vector that is going in the opposite direction, we're just going to make this negative. So I get -4, -8. And then I want half the size of the vector. So if I have this vector of 2, 4, half the size of the vector in the opposite direction is going to be -1 and -2. Moving on. So number 6, it says, find the unit vector in the direction of 2i, negative 3. Well, what's the size of this vector to begin with? The size of this vector is the square root of 2 squared minus 3 plus minus 3 squared. So that's going to give me the square root of 2 squared, which is 4, plus 3 squared, which is 9. That's going to give me the square root of 13. So right now we have the magnitude, or the size of this vector, is the square root of 13. And I want a unit vector. It says find a unit vector. A unit vector is a vector with a magnitude of 1. A vector with a magnitude of 1. So, well, if I have a magnitude of the square root of 13, what if I divide this vector by the square root of 13? Well, we can't divide in vector space, so we're going to multiply by 1 over the square root of 13. So 1 over the square root of 13 times this 2i minus 3k. This vector now here has a magnitude of 1. All right, let's do another one. So I want to find the size of this vector. We have 2 squared plus negative 2 squared plus 1 squared, all under the square root. So that gives us the square root of 4 plus 1. We have 4 plus 4 is 8, plus 1 is 9. So I have the square root of 9, which is just 3. So right now, this vector right here has a size or a magnitude of 3. So I'm going to take this vector and I'm going to just multiply by 1/3. So I have 1/3 times this vector of 2i minus 2j plus k. This is my vector now going in the same direction with that's a unit vector with a magnitude of 1. All right, number 7 says, find a vector v which has the opposite direction of negative 1, negative 4. So that would just be 1, 4 going in the opposite direction. And it says a length of 2, so that our magnitude is 2. Well, what is the size of this vector right now? The size of this vector is the square root of 1 squared plus 4 squared, which is 16 plus 1, 17. We're looking at the square root of 17. So let's make this a unit vector. A unit vector then is going to be, our scalar is going to be 1 over the square root of 17, and we're going to multiply by our vector here of 1, 4, or we have 1 square root of 17 for square root of 17. So either way is fine, but this is our new vector here of, well, with a unit vector. It right now has, it's a unit vector or a magnitude of 1. Now if we take this vector of a magnitude of 1 and we multiply by a scalar of 2, then that's going to give me, that was 17 for square root of 17. That's going to give me 2 square roots over 2 divided by the square root of 17, and 8 over the square root of 17. So there you go. Now this is a vector that's going in the opposite direction of this negative 1, negative 4 with a length of 2. Yeah, just running out of time. We're going to move down to 9b. So it says, find the vector of length 2 units which are parallel. So I guess we're looking at which is plural. So find vectors of length 2 units which are parallel. So we're looking at vectors that are going in 2 different directions. It doesn't say opposite, and it says are, so it implies 2 different vectors. So let's find the size of this vector, or the magnitude of this vector to begin with. So we have the square root of negative 2 squared plus negative 1 squared plus 2 squared. That's going to give us, negative 2 squared is 4. 4 plus 1 plus 4. That gives us 9. It's the square root of 9, which is going to be 3. So right now we have this vector here as a size or a magnitude of 3. And now let's scale it down to I know we're looking for a unit vector of 2, but let's reduce this to a unit vector of 1. So we're going to multiply by then 1/3. So that's going to give me 1/3 of this vector, -2, -1, 2. I should point out that because we're looking at two vectors that are parallel, we could be going in either of these directions. So I'll make it negative and positive. So we could just leave it like this if we wanted to, or we could rewrite it like, well, I actually think this is the easiest way to leave it because we have this positive and negative. I guess we could actually write out the two different vectors. We have negative, let's do the negative variety first. So I have negative 1/3 times -2, which is going to give me positive 2/3. I have negative 1/3 times negative 1, which is going to give me positive 1/3. And then negative 1/3 times 2 gives me negative 2/3. So there's one of our vectors. And our other vector, we're going to use the positive variety. So 1/3 times -2 is going to give us negative 2/3. We also have 1/3 times -1, which is going to give us negative 1/3. And we have 1/3 times 2, which is going to give us 2/3. So this is our second vector. We have two different vectors going in opposite directions. All right, last problem. So it says here, find a vector b in the opposite direction of this vector -1 to -2 with a length of 5. So it's really the same concept. We're going in the opposite direction, so we're going to reverse this. We have 1, 2, 2, and we're going to, if we need to find a vector of a length of 5, let's find the vector of a length of 1. So the square root of 1 squared plus 2 squared plus 2 squared is going to give us 2 squared is 4, plus 4 is 8, plus 1 is 9, so I have the square root of 9, which is just 3. So if I multiply it by a scalar of 1/3, then I have a unit vector. So now I want a length of 5, so I'm going to multiply by 5. So that's going to give me 5/3 times this unit vector here, and which is fine. We could just leave it like this. So 5/3 of this, it's not a unit vector. This is a vector of size 3. So this now is a vector of size 5. So 5/3 times 1 gives us 5/3. 5/3 times 2 gives us 10/3. And 5/3 times 2 gives us another 10/3. So I'm okay with this being your answer, but this is also our vector here. All right, I hope this was helpful, and have a wonderful day.